Hello, welcome to the Lionheart Academy. This is Richard Tai. Today we're going to talk about a certain technique, integration technique called the U substitution in calculus. We're going to talk about a basic technique, and so hopefully this lesson, this video will be able to help you become better and then understand a little bit more about U substitution. Right. So before we start, what is U substitution? Well, sometimes when we deal with integration problems, they are a little bit more complicated than the straight integration problems that we usually use. For example, the one that we usually can use power rules for, or the other ones that we can use trig identities, or not trig identity, I'm sorry, just trig integration rules for. There are also the simple ones like polynomials, or saying that maybe even some of the mostly the power has to do with power integration using the power rules. So besides those, there are other things that are more complicated. So this is basically the first technique that we are going to need to know to help us enhance our integration techniques, help us understand a little bit more how to do integration. Now, so this technique, U substitution, actually is very similar to the reverse of chain rule. So in derivatives, chain rule, okay, so if you, let's go ahead and just review a little bit about chain rule. Okay, so when we do a chain rule is when we take the derivative of a composite function. So for example, we have f of g of x. So g of x is the inside function and f of x is the outside function. And so when we take the derivative of a composite function, we need to take the derivative of the outside, but we also need to take the derivative of the inside function. So this is called the chain rule. So it would be f prime of gx times g prime of x, which is the derivative of the inside function. And so the chain rule is the basis for our U substitution. Okay. Now, let me go ahead and take a look at let me give you the U substitution rule first. Okay, so let's say if we have the integral of fu du dx. So we're integrating fu du dx, and then we're integrating in terms of dx. This will simply be equal to fu du. Alright, let's see. Let's talk a little bit about how this becomes true. How this is true. See if we can understand this process. Alright, so let's consider the function f. Okay, so f is the antiderivative, capital F is antiderivative of function little f. Okay, so let capital F be the antiderivative of function f. So when we take the derivative in respect of u of f of capital F of u, what we're going to get? Well, if capital F is the antiderivative of f, so when we take the derivative, we're just going to get f of u. Okay, so that's pretty straightforward, right? Alright, now let's think about the opposite. So if you integrate lowercase fu du, what we're going to get? Because, again, capital F is the antiderivative of lowercase f, so we're going to get capital F back. Capital Fu plus an integration constant. Okay. So, now the next step is if u is a function of x. Okay, u is a function of x. So if u is a differentiable function of x, that means u is a composite function, or actually f of u is a composite function, because u can be expressed as a function of x. Then let's go ahead and take a look at this expression again. So when we take the derivative, then we can take the derivative of x in terms of x of f of u, which will be du, right? When we apply chain rule, because u is the inside function, right? So we take the derivative of f of u, and then the derivative of u, we have to take the derivative of u in respect of x, which is du dx. Okay, and the derivative u of fu is, as what we have seen, is just f of u du dx. So this is a chain rule. We took the derivative of the outside function, which is capital F of u. It will give us lowercase f of u, and then we take the derivative of the inside function, which is u, in respect to x, which would be du dx. So that means now we can go ahead and show that now if we integrate this expression, capital F of u du dx, okay, if we integrate this expression in respect to dx, then that will give us back what we started with, which is capital F u plus c. So that is the basic concept for the integration by parts. So, of course, that's all a lot of letters and symbols, but this is to help us develop. If you understand this thought of logic, then this will help you understand how everything goes. Again, basically, U substitution is just a reverse. It's kind of very much like a reverse of the chain rule. So, that's that. And so, let's go ahead and take a look at some examples. Okay, and then hopefully we will be able to look at some concrete examples to help you understand what's going on. Alright, so this is looks like a very complicated expression. It says x squared plus 1 quantity to the 50th power times 2x, okay, dx. Now, if we don't know how to use U substitution, we would have to expand this to the 50th power and then times 2x, and then we can integrate each individual terms individually. But that is not very efficient. So that was not going to be very efficient, right? So we rather not do that. Now, in this case, we are going to look for something. We're going to try to see if we have an inside function and an outside function. Now, the key looking for the inside function is that the expression dx has to be there must be an expression that is equivalent to the derivative, or equivalent, or is something that we can make into a du dx. So I look at this expression and I say, oh, okay, there's x squared plus 1 to the 50th power. So this is a function, and then this is raised to another power, so that means it's a composite function. And then on the outside, I see a 2x dx, and then I realize that the derivative x squared plus 1 is 2x. So if I take if I let u, okay, be the inside function, in this case is x squared plus 1, then the derivative u in respect to x will be 2x dx. And then we look at this, yes, I have 2x dx. Okay, so we're going to let this be our u, and we're going to let 2x dx be our du. So when we replace this expression, now we can replace x squared plus 1 with u, so it becomes u to the 50th power times du. So that's our substitution. We just use u to substitute in terms of x. Now we can integrate this expression much easier, because there's only one single expression. We can use the power rule in a sense, okay, when we integrate a power expression. So it's going to be u to the 51st power divided by 51 plus an integration constant, okay. Alright, so but the answer cannot be left in u. Why? Because we started with an integration in terms of x. Well, what do? Well, we simply, after we got the expression, after we done our integration, we simply replace u with what in terms of x again. So we replace u with expression in x. So here it's going to be x squared plus 1 to the 51st power divided by 51 plus an integration constant c. And that is that. That is as simple as it is. So the key, again, is to recognize the inside function and the outside function. What is inside, what is outside? So in this case, this is the inside function. And the key of recognizing inside function is out on the outside. Before the dx, we should be able to make a du. So what you can do is you select an expression for the inside and then take the derivative of that inside expression u and find out and look at this to see if it's possible for us to come out with a du. Now of course du may not always be there, so let's go ahead and try some other examples. Okay, now let's go ahead and try this. Sine square x cosine x dx. Okay, alright, so for sine square x cosine x dx, which one should we let our u be equal to in this case? Well, I see we have sine x to the second power, so it seems to be a function within a function. It seems to be a composite function, and I know the derivative of sine x is ux, so let's go ahead and try this. And we do have a cosine x outside, so let u equal to sine x. So if u is sine x, the derivative of u with respect to x will be cosine x dx. Alright, I see we do have a u here. Okay, so let this be our u and let this be our du, right? So let's replace u and we will get u squared because u is our sine x, right? So sine x will be u squared times du. Oh, that is very easy to integrate. We just go ahead and add 1 to the power and divide by 3 plus an integration constant. And at the end, the last step is just to replace the expression, original expression. So it will be sine to the third power x, sine x to the third power divided by 3 plus an integration constant. Okay. Alright, let's try another example here. Now we have cosine square root of x dx divided by 2 square root of x. Now on the surface, it seems to be kind of weird. It's like, how do I do this? Which one should I be my u? Should I let u be cosine of x, or should I let my u be square root of x? Well, if I want my u be cosine of square root of x, then that will be this is actually a composite function. As you can see, inside function is actually square root of x, outside is actually cosine. So generally speaking, we would always want to use the inside function first. So let u be equal to square root of x first, and let's see how we can take the derivative of this. Now, so what's the derivative of square root of x? Well, we're going to treat x as in the power form as x equal to 1/2. So then we take the derivative using a power form, so it's 1/2 x to the negative 1/2 power. Now a negative 1/2 power is the reciprocal of positive 1/2 power, so it's 1/2 to the square root of x dx. I forgot to write dx here. Okay, so yeah, actually I do see that, do we? dx over 2 square root of x. Yes, we have that. So that means this expression is going to be cosine u, and dx over 2 square root of x is going to be du. And we know how to integrate cosine u. Cosine u is the integral of cosine u is sine u plus a constant. Okay, and then finally the last step is to replace u with expression x, so sine square root of x plus c. That's it. So here we have tried several simple examples. Now let's go and try something a little bit different. Alright, x squared square root of x cubed plus 4 dx. Okay. Alright. Now there are so many things here. You have x squared times square root of x cubed plus 4. Now square root is a function by itself, but inside has x cubed plus 4. So I would think that I want let x cubed plus 4 be equal to my u. However, you might say that that's not going to work because the derivative of x cubed plus 4 is 3x squared, but I only have 1x squared. Well, 3x squared and 1x squared, we can go ahead and actually make that work. So let's go ahead and write this down. So let x equal to x cubed plus 4. So the derivative of du in respect to x is 3x squared plus 0 dx. Okay, so I need a 3x squared dx, but I don't have a 3. What do? Well, what I can do is, because all I need is a constant multiplier, so I can multiply by a 1/3 and I can multiply by a 3. The reason is I can do that is I'm actually multiplying by 1. Because you take a look at this, if I multiply 1/3 by 3, it's 1. But I'm just basically multiplying by a 1 and I'm expressing the 1 in 2 different factors. Okay, so then after this I can recognize, okay, this is going to be my u, so it's going to be square root u, and 3x squared dx is going to be my du. So, but then I'm ending up with, I'm having a 1/3 factor in front of it. That's to take care of this 3. We're missing that 3, right? The original multiple equation doesn't have the 3 there, but we can multiply by a 3 inside and multiply by 1/3 on the outside. So then let's go ahead and integrate. Now, square root of u is square root of 1/2 is u to the 1/2 power. So if you go ahead integrate, it will be u to the 3/2 power divided by 3/2. Okay, plus a constant. So let's go ahead and clean up the downwards here. It's going to be 2/9. Okay, when you divide by 3/2, you multiply by the reciprocal. So it's 2 to the 3/2 u to the 3/2 power 2/9 times u to the 3/2 power plus c. And then we should simply replace u with the expression of x cubed plus 4. So it will be 2/9 of x cubed plus 4 to the 3/2 power plus c. Alright, so let's look at another example similar like this. Example 5. Okay. Alright, cosine of 5x dx. Okay. Now this looks very simple. It seems that, oh, shouldn't this just be cosine of integral of cosine 5x? Shouldn't it just be sine 5x? Well, not really, because 5x is a composite function of x. It's not really just x. So we're not integrating cosine x, we're integrating cosine 5x. So the inside function is 5x. So let u be equal to 5x, and du would be equal to 5 dx. So I see that, oh, again, I do not have a 5 dx. But what we can do is we can only multiply by 5/5, but I just write the 5/5 differently. I write the 1/5 on the outside, and I write the 5 on the inside. So I multiply by 5, but I also divide by 5 at the same time. So I'm really just multiplying by 1. I'm not changing the value. I'm just writing this differently. So 1/5, okay, this becomes cosine of u du, okay, 5 dx becomes du, and the integral of cosine is sine, so sine u plus a constant c, okay, and what do? Well, we go ahead and do 1/5, and then lastly just go ahead and replace u with 5x plus c. So as you can see, the final answer is 1/5 sine x 5x plus c, not sine 5x. Okay. Okay, so far all the examples we have tried are indefinite integrals. What about definite integrals? When we do definite integrals, let's go ahead and try this. 0 to pi over 2, the sine of, let's do pi x, okay, pi x dx. So let's go and try to integrate this. Now, this is the lower limit and this is the upper limit, which is x equal to 0 to x equal to pi over 2 sine pi x dx. So the inside function is very similar to the previous problem we have. So let u be equal to pi x. And so du is going to be equal to pi dx. Okay, so we know that we are missing a factor of pi, but we can use the same method here. We multiply by pi over pi, but we write the pi. The numerator pi, we go ahead and write the inside the the integral. So we write the pi again, write the pi inside the integral, the pi dx. Therefore, we have a u. Now I forgot to put the limit here, 0 and pi over 2. Alright, so now we're ready to do u substitution, except one thing is that the limit is going to be different, because if we replace this with u, sine u, du, we're not integrating from 0 to pi over 2. Why? The reason is that is the x boundary, the x value for the upper bound, lower bound. So what we need to do is we need to solve what is u when x equal to 0. So what do? Well, we know the relationship because u is pi x. So when x equal to u, when x equal to 0, u is equal to 0. And then when x equal to pi over 2, okay, u is equal to pi squared. Pi times pi over 2, which is pi squared over 2. Okay, this is pi squared over 2. Alright, and then we divide by 1 over pi on the outside. Alright, so now we're ready to change to u equal to 0 and u equal to pi squared over 2. Sine u du. Alright, so now we can go ahead and integrate this. So when we integrate this, this will be negative cosine u. And instead of plus c, we're going to use our lower bound, upper bound 0 and pi squared over 2. Okay, so this will be 1 over pi on the outside. Okay, negative cosine pi squared over 2 minus another negative cosine of 0. Okay. One more of this. So let's go ahead and evaluate this expression and see what we'll come up with. Alright, so after we type in the calculator, we get approximate decimal 0.2481. Okay, so that's the decimal for this integration, and we integrated by using U substitution. Now there's a second way to approach this, so let me go ahead and show you that that we don't have to use U. What we can do is instead okay, so let me go ahead and write it down here. So instead, when we have 1 over pi, right, of 0, this is, let me write x equal to 0, and then upper bound is x equal to pi over 2. Alright, and we integrate sine u du. Okay, so just be careful. I'm not going to plug this in. Now I know this may not be a correct formula, but one thing is we can do is after we go ahead and then integrate it, we got negative cosine, right? We got negative cosine. So I'm just going to ignore the lower bound, upper bound for now. Okay, I'm sorry. I'm going to ignore the lower bound, upper bound for just for a minute here. Now, after we integrate it, we should get negative cosine u, and we should be substituting u, the lower bound of u and lower bound of u, right? Upper bound of u. So u should have been equal to 0, u should have been equal to pi squared over 2 here. So, but instead of doing this, I can bypass this this substitution. I can go ahead and directly use x. I substitute u back to x. So what is x? Is cosine of pi x, right? So then the lower bound limit and upper bound limit will go back to x, which is like this. So x equal to 0 to x equal to pi over 2. So the advantage of this is I don't have to calculate the lower bound of u and upper bound of u. I can go ahead and integrate it and then replace u back to x. And then let's go ahead and try what will happen here to see if we get the same answer. Well, if we should, if we do it correctly. So it will be cosine of pi squared over 2, right? When you plug in pi over 2, minus negative cosine of 0. Okay, so let's see what happens here. Well, as you can see, actually, I don't have to calculate it. Look at the, if you look at the few lines before, look at this section. Well, they are the same line. They are the same line, so that will give you the same number, 0.02481. So this is another way to do it if you don't want to calculate the lower bound, upper bound of u. But you just have to be careful. When you do this, you have to remember to replace u back with x, then substitute the lower bound, upper bound of x. Now, this method depends on which one you prefer. Either way will work. Either way will work. And then if you do it correctly, you all will get the same answer. So, alright. So, I hope this lesson of U substitution will help you in understanding a little better. If you have any other questions or comments, please leave your question comments in the comment section below. And then we look forward to sharing with you more skills in our lessons in calculus and trigonometry as well. Thank you.